Hi, welcome to our 5 o'clock press conference, The Impacts of Heat Stress on Densely Populated Regions in the 21st Century. Our speakers are Ethan Koffel, PhD candidate at the Center for Climate Systems Research at Columbia University, Radley Horton, Associate Research Scientist at the Center for Climate Systems Research at Columbia University, and Noah Diffenbaugh, Associate Professor at Stanford University and Senior Fellow at the Woods Institute for the Environment.
All right, so in recent years, heat stress has gotten a lot of focus as an impact of climate change, but many studies have focused on air temperature alone, which is projected to rise dramatically. But when considering the impacts on people directly, it's important to take into account humidity as well. So the combination of temperature and humidity is heat stress, and this can be measured by a variety of indices. The one that we choose to use is called the wet bulb temperature. And so this can be thought of as a measure of the efficiency of evaporation. So humans cool themselves using evaporation, the evaporation of sweat. And when the relative humidity is low, evaporation is efficient, and so the system can cool you quite well. But as humidity rises, the evaporation efficiency declines, and so the ability of people to cool themselves also declines quite rapidly. So in 2010, there was a paper published projecting a theoretical limit for human tolerance to heat stress in reference to the wet bulb temperature. And they calculated this limit to be 35 degrees Celsius. In the current climate, 35 degrees Celsius wet bulb temperatures are basically unheard of. Recent heat waves, like in the US in 1995, Europe 2003, Russia in 2010, and the Middle East and India and Pakistan this year produced wet bulb temperatures in the range of 29 to 31, and still produce dramatic impacts on human health, infrastructure, economic performance, and agriculture. So as climate change progresses, wet bulb temperatures are projected to dramatically increase. And we used the CMIP5 model suite along with population data from the Shared Socioeconomic Pathways project to project exposure to wet bulb temperatures that exceed 31 degrees Celsius. And by the 2060s, our results show that hundreds of millions of people could potentially be exposed to wet bulb temperatures of 32 or 33 degrees Celsius. And these wet bulbs are extremely high and may make outdoor work difficult or impossible. So the main regions at risk of these wet bulb temperatures are in India, the Middle East, and West Africa. So there's variability in these results year to year. But this variability mainly comes from the fact that heat waves may not hit the most densely populated regions in a given year. But we think of these results as showing the order of magnitude number of people who are at risk to experience these kind of events. And our results indicate that heat stress needs to be taken into account in climate adaptation planning.
Is it okay to talk from here? Okay, great. Okay, so I thought I would talk a little bit about some of the broader implications of the study and some future directions for research in this area. So the place to start, clearly, in terms of impacts, as Ethan mentioned, is public health. In the ideal context, people who are perfectly fit in sort of the best possible outdoor conditions, we have that 35 Celsius threshold. But of course, many people have pre-existing health conditions. We have people who are very young, we have the elderly. All these people are going to be vulnerable at much lower temperatures. Who else is going to be vulnerable? Anyone doing strenuous labor outdoors. Obviously, in large parts of the world, people spend the majority of their time outdoors. Agricultural workers, for example, often in very strenuous conditions. That's going to increase the vulnerability as well. So that even before we get to those 35 Celsius temperatures, we're already seeing some of those vulnerabilities. And some of the recent high heat and heat stress events have already begun to show some of that vulnerability of human health. Energy and infrastructure, I think the place to start here has to be with the power generation required for air conditioning. As we get to more and more of these situations with very high wet bulb situations, basically we're going to have conditions where the power systems and air conditioning can't fail. You can't afford to have them fail. With these high heat stress events occurring more often, lasting longer when they occur, covering bigger areas, those all suggest the potential for large nonlinear increases in air conditioning demand, possibly at the same time where air conditioning performance may not be as successful because of that high moisture in the air. It poses some technical challenges to just the efficiency of air conditioning. How about economics and labor productivity? We talked before about all the outdoor laborers. This is a big population everywhere, maybe especially in some of the developing countries where vulnerabilities are higher for a variety of reasons. So if we think about agricultural workers who won't be able to spend as much time outdoors in the heat of the day in the future, for example, construction workers, what are the impacts on the economy? Maybe if they are able to work, it's going to need to be fewer breaks, there'll be impacts on productivity. That's sort of the most obvious effect, but of course anytime we're talking about economic impacts, we need to think about cascading effects, supply chain effects across regions as well. And then I think a bigger wild card is ecosystems and large mammals especially. Large mammals share some similarities with humans in terms of their potential vulnerability to very high heat stress. So that's something where further research is needed as well. So in terms of that future research, key questions. Getting into some of those public health impacts in more detail, as we look at subpopulations, those with cardiovascular disease, those with respiratory diseases, how will they be impacted? The very young, the elderly, critical areas for future research. Are there differences in different parts of the world in terms of maybe societal factors that influence exposure and vulnerability? What are some of the climate factors that could impact our results? These results were generated using global climate models. What might happen at finer spatial scales that could impact these results? Local ocean temperatures can be a really big driver of the extent of these high heat humidity events. How far inland away from the coasts will we see some of these really deadly high heat and humidity events penetrating? And will the climate system respond in some ways that surprise us? Will we see changes in the nature of motion in the atmosphere, more convection in the atmosphere, rising air in a way that might change and potentially ameliorate some of these worst case scenarios? Those are big open research questions. Another issue from this risk perspective, if we're trying to consider worst case scenarios, how might high heat and high humidity interact with other climate hazards? Is there going to be a correlation with bad air quality? Could that increase people's exposure if you're getting these really high heat humidity events happening at the same time people are exposed to small particulate matter, for example? What could be the correlations, the relationships to other variables? Will you tend to see more of these kind of events after heavy rain events that have already created vulnerabilities for populations? Those are big unknowns, but if you're thinking about risk, if you're thinking about worst case scenarios, we need to think about possible relationships in space and time that could either increase the risk or decrease it. I mentioned earlier how other species will be impacted. I think that's a big open research area. And then how can we prepare, right? That's sort of what this all comes down to in a sense. Greenhouse gas mitigation, obviously, the starting point here when we start talking about absolute thresholds that we don't want to cross. But in the sense of adaptation as well, what can be done? This, as I said earlier, this suggests we need more reliable power and air conditioning systems, including for many parts of the world where people don't have air conditioning today. Additionally, are we going to see potentially changes in behavior, more working during the overnight cooler hours, more breaks, less strenuous activities at certain times, maybe changes in clothing that are worn, things like that might be able to help some of these issues to some extent. More extreme scenarios potentially, will this impact where people are living at some point in the future? Are we as a community possibly starting to hone in on another source of coastal vulnerability near very warm oceans that's distinct from the sea level rise and coastal flood threat that's received so much attention in recent years? I think clearly the science is less far advanced on this issue. As I've highlighted, there are a lot of uncertainties, but I think we've exposed a potential high vulnerability that's worthy of further thinking. Thanks.
Sure. Okay. Hi, I'm Noah. I'm not part of the study. I'm here as the outside person. I have worked on severe heat, and including one attempt back in 2007 to try to integrate the effects of temperature and humidity, in that case focused on the Mediterranean region. I'd like to say that I think what these authors have done is a considerable step forward from the work that we did back then in terms of how they've integrated moisture and temperature together. So I'm happy to talk about those details if there's interest. I think overall, I think this is a big step forward in that, as was mentioned, we've seen attempts to really try to look at what is the source of impact of climate on natural and human systems as a broad research area. And this is a case where the authors have really targeted the most immediate, most acute interface between climate and people. And I think that highlights really where we need to go in terms of our understanding of climate impacts, both in the current climate, the 1 degree world that we already live in. We've already had 1 degree Celsius of global warming. We're already living in a different climate. We're already experiencing impacts, and whether coming out of Paris, whether the world ends up at 2 degrees of global warming or 1.5 degree of global warming or more than 2 degrees, it really is going to be this interface where the climate system really hits most directly. And we heard a lot about those various the ways in which the effective temperature, the heat stress really impacts. It often turns out to be the extremes, and I want to applaud the authors again for focusing on not on the mean climate, but on the extremes, and that's where that's where we often see these big events, and it's often the co-occurrence of different conditions where we see big impacts. So, for example, a couple years ago in India, with severe heat and the electric grid not being able to handle the demand at the same time, we saw big impacts. The derecho a couple years ago in the Northeast. And so I think I would echo what's been said about not only human vulnerability, but also what we rely on to protect ourselves from climate extremes in terms of air conditioning in this case being one, but also as we heard already, just kind of the way everything is set up in terms of when people are working outside, the way that economic activity is set up. This is an example where climate change potentially can change, or the impacts can really be a function of what we've set up for the current climate no longer being optimal for the new climate. And I think the key there are extremes and interacting physical hazards with exposure and vulnerability. So I'll stop there.
Okay, great. We'll open the floor to questions. Any reporters who have questions, please state your name and affiliation.
Mark Pichetti, Scientific American. Just two basic mechanism questions. What's the assumption that humidity is going to go up based on? Radley, you mentioned warmer seas, but is it that? Is it higher temperatures, more precipitation, or more evaporation? And the other mechanism, what happens to the body at 35 wet bulb temperature that we can't do anything else beyond that?
So the first part, so in general, specific humidity, which is the absolute amount of water vapor in the atmosphere, is projected to go up as temperature rises because warm air can hold more water. But also as temperature rises, relative humidity, which is what's normally reported on weather broadcasts, goes down because relative humidity is a ratio of the amount of water in the air to the maximum possible amount of water in the air. So on a hot day, as temperature rises, relative humidity falls. And so there is sort of a point at which you reach the maximum heat stress. And it's a competing effect between the falling relative humidity and the rising temperature. And so in most cases, the maximum heat stress occurs before the maximum temperature occurs. So we can get these extremely high heat stress values. We get them a lot in coastal locations where you have sort of onshore flow from very warm ocean waters that brings humid air over land. And so like this has occurred now in the Middle East, in coastal cities there, where you have desert heat combined with this humidity coming off of the ocean. And you can get a very unusual combination of extreme temperatures and also high humidity values. So many of these high heat stress values are projected to occur in coastal areas. And so that's the primary mechanism by which this happens. So it's not really driven by increases in humidity, it's mostly driven by increases in temperature. And so these can occur in regions where the humidity stays relatively high or higher than it normally would be. So the second part, I'm not sure that there's really any data on this. These temperatures basically don't occur at the moment. So in theory, 35 wet bulb is the point at which more or less your sweat will not evaporate. And so your body produces heat, and if you can't evaporate your sweat, you can't cool yourself. And so heat would build up, and presumably after some amount of time, you would experience heat illness. And so the amount of time that this would take is, it depends on how hot it is and also what you're doing in particular. So any kind of physical activity, even light physical activity, would probably significantly reduce this threshold at which heat would become dangerous, as we see in recent heat waves when tens of thousands of people have died at wet bulb temperatures that are much lower than 35.
Rick?
Yeah, sorry, I was taking a quick note on the last one. Rick Lovett, freelance. So I'm more familiar with wet bulb globe temperature than with wet bulb temperature. So you're not taking sunlight into consideration in this, and I'm wondering what the models show about increasing clouds and therefore reduced radiative heating. I'm also, very technically, can you give us some examples of what would be a 35 degree or 34, whichever the number was, wet bulb temperature? Because 95 degrees and high humidity is something we get a lot of where I've lived in times of my life anyway. So it doesn't sound that horrid. So I'm guessing it's something different than it sounds like.
Yeah, so the first part, so the wet bulb globe temperature is an index that's used to measure heat stress, in particular in the military and in athletics and in industrial, like workplace safety applications. And so this is it's really an empirical index. It's a weighted average of the air temperature, the wet bulb temperature, and also the globe temperature, which is sort of a non-standard meteorological measurement, which takes into account radiation intensity, more or less. So this is higher in direct sunlight and less in the shade. So the wet bulb globe temperature is, there are thresholds at which people have been observed to start experiencing heat illness, but it's entirely empirical. And so we don't use it because the wet bulb temperature itself is a more physically based measure, and this threshold of 35 degrees Celsius is not empirical. It's a theoretical calculation of entirely to do with evaporation. And so we think this is a more physically based and less experimental measure of heat stress on humans. And so the other thing is that incorporating radiation is hard to do in a model application. So cloud cover, whether it exists or not, is hard to model. And so we get better results using the traditional wet bulb temperature. Sorry, could you repeat the second part again?
Examples of what...
Right. Yeah. So basically, there are two known situations where the wet bulb temperature has approached 35 Celsius, and they occurred in the Middle East. So once in Iran last year, and then once in Saudi Arabia a few years ago. And so they required, I believe the air temperature at both of these was in the range of 120 degrees Fahrenheit, and the dew point was in the range of 90 degrees Fahrenheit. So that's like very extreme conditions that never even come close to occurring in the US. So the wet bulb temperature of 35 C, or about 95 Fahrenheit, it's not like a air temperature. It's really the minimum temperature that an object could get through evaporative cooling alone. So a wet bulb temperature of 35 C is extremely high, and it's almost unheard of in the current climate.
Are there any other questions in the room? Are there any questions on the chat?
Yeah. This is Harvey Leifert, freelance for Environmental Research Web. For Dr. Koffel, can you explain the formula for determining the wet bulb temperature from the Celsius temperature and the relative humidity?
So we use an empirical model of to calculate wet bulb temperature from relative humidity and air temperature. And so there's a paper published a few years ago by Stull that produces this, or that they present this model, which was shown to have quite low error in estimating the wet bulb temperature from just relative humidity and air temperature.
Okay.
Well, I'll ask another, although if you give him first.
Oh, George Drake, Tall Mountain News. Excuse me. Can you give examples of the approximate wet bulb data that would go with the East Coast humidity events?
So probably in the most extreme heat waves that occur in the current climate, you might see wet bulb temperatures in the upper 20s on the East Coast, so say 28. So maybe 28, maybe 29, but probably never above 30. 30 is about the limit in the U.S. that we experience these days.
Okay, so Rick Lovett, freelance again. So you kind of implied that some areas might become uninhabitable, and I want to push you on that because that's kind of I mean, are people going to have to move out of some places if we don't control global warming on this, or will we find, or will we just air condition everything, or how bad? I think I saw a stat up there that said 50 million people might be forced out of their homes. Did I read that right?
No, we didn't have a statistic saying that. We had statistics showing how many people might be exposed to these really high wet bulb temperatures above 33 Celsius, a number of about 250 million per year. I think to some extent that's a societal question. What are the opportunities to respond? That's going to depend on the extent to which we see some of these adaptations that we talked about. It's going to depend on the extent to which we might see shifting towards more nighttime activity, reliability of air conditioning for sure. Also, is there a role for insurance markets potentially? Is there a role for a private sector in helping to hedge and protect against some of these risks? I think those are some of the kind of factors that could ultimately impact whether or not people end up moving to a large degree. But I think it's a risk that we can't rule out.
I would add, I think, getting back to the risk, really being the interface between the physical conditions, the exposure, and the vulnerability. It's really that intersection that creates the risk. And what we're seeing in this analysis is analysis of the probability that the conditions exceed some of these biological limits that were discussed. But we do a lot to manage our relationship with the environment, even in the current climate. And so, air conditioning and shelter, and so I think as we heard, the question is really how do we prepare for these changes if there's a priority to try to get out in front of these changes. Then, we saw in the last World Cup, FIFA allowed water breaks during matches. So there's one example of making a change to decrease vulnerability. I don't want to trivialize it, but if you imagine the scale of what's being discussed in these results, that's much larger than exerting oneself in the summer in Brazil. But I think that the bottom line is that we have tremendous ingenuity in the current climate. We see people living and thriving in an extremely large range of climatic conditions, and we see people that are highly vulnerable to that range of climatic conditions. And the question is really, what are the risks and for whom, and how do we how do people choose to address those risks with the acknowledgement that we're on a pathway towards continued global warming, and even with even with the agreement in Paris, that agreement bakes in further global warming. We're already seeing unprecedented extreme events. We're seeing unprecedented heat events. We're seeing them have impact. We're going to face those physical conditions, those hazards, more frequently in the future, and it's really how we manage not only how much global warming there is, but also exposure and vulnerability that will determine what the ultimate impacts are.
Are there any other questions from reporters in the room? Oh, here you go.
Are you recommending that preparation for this be done now as opposed to wait?
Well, I think heat causes damage right now in the current climate, right? And we've heard about some of those particular events. Europe in 2003, there was a very clear demographic and geographic pattern to who died during that event, and the role of early warning systems, the role of response during the event. Those were really important in determining, of those that were vulnerable, who ended up really being impacted in a big way. So I think it's clear that we, in the current climate, in many cases we're doing well. I mean, if you take being protected against these extreme events as a measure of doing well, we're doing well in many cases, and there are many cases where we're not. So I think given what we've already heard about the statistics of extreme heat in the current climate and the impact that severe events have, there's room for society to better protect itself in the climate that we have now. And we have very robust scientific evidence that those kinds of events will become more frequent and more severe as global warming continues.
Are there any other questions in the room? Are there any other questions on the chat? Okay, thank you very much. That concludes our press conferences for today. See you all tomorrow.